Hi everyone, it's Mr. Hamilton here, and welcome to this video on Oersted's discovery and solenoids. We're going to look at what Oersted discovered with the relationship between electricity and magnetism, and then we are going to look at solenoids, which are basically just coils of wire, and how those apply to the idea of electromagnetism. So Hans Christian Ørsted was a Danish physicist, and he was born in 1777, died in 1851. And so one of the things that made him unique was that his discovery was actually done during a lecture. A student showed him something at the end of the lecture and allowed him to see something that he'd never seen before. So let me give you a couple other historical backgrounds before I get to the handout. The first thing is this. They knew that everyone knew at the time that if we're going to have electricity, two things have to happen. We have to have heat and light. There's going to be some connection between heat and light. That was their experience with electricity at the time. And what was known as well is that if we have certain ships that get struck by lightning, not a good thing to happen, but the HS Suzanne was struck by lightning. And what happened is the compass was affected very briefly. The polarity of that compass was reversed very quickly. And so something peculiar was happening here. The thought was this. The thought was that if we have a current-carrying wire, and we bring a compass up to that current-carrying wire, and let's say the compass points north, because the north is in this direction, then we turn the current on that wire, shouldn't we see this compass point away? The thought was that that compass is going to spin, and it's going to point in this direction away from the wire. That was the understanding, that if there was this idea of electricity connected with magnetism, that the magnetic field would radiate away from the wire. But that is in fact not what happened. In fact, every time that we brought the compass close up, every time that Ørsted or another physicist brought it close up, it would stay pointing north, which seemed to suggest that there was no connection between electricity and magnetism. However, they weren't quite onto it properly. What was actually happening is that if we have a current-carrying wire, the magnetic field, as we'll find out in more detail very shortly, is actually formed in concentric circles around the wire. So this is what we call the right-hand rule. We put our thumb in the direction of the current, so there's the current in the wire, and our fingers wrap in the direction of the magnetic field around the wire. And that was discovered during a lecture in 1820 by Hans Christian Ørsted. So let's go on and look at a little bit more now of the mechanics of how this works. Ørsted did indeed discover that a moving charge creates a magnetic field. And so this is the basis of electromagnetism. Electromagnetism is when we have a magnetic field produced using an electric current. And we can actually do the opposite as well. We can use a magnetic field to produce an electric current in a wire, as we'll find out as we go on with this unit. Ørsted's principle was this. A charge moving through a straight conductor produces a circular magnetic field around the conductor, or concentric circles of magnetic field around the conductor. So just a couple of conventions we need to be familiar with first. This is the first one here. If we have current flowing out of a page towards us, so there's a wire, the current is flowing directly out of the page towards us, then it's like an arrow is being shot at us. We see the tip of the arrow coming towards us just in the form of a dot. And then if the current is flowing into the page, so if that wire is going with the current, conventional current again, into the page, then it's like we're seeing the back of the arrow, where we see the feathers in the back of the arrow, and it forms an X. So that's the first convention that we need to be familiar with. Currents in a wire form magnetic field around a wire that's circular with the wire at the center. So the right-hand rule, I already said this, but now we have it written down and we can just go over this. Yes, don't use your left hand. Someone out there is taking their left hand trying this. Make sure you have your right hand, all right? You're going to grab the wire with your right hand, and the thumb is pointing the direction of the conventional current. So someone's making the connection here. Well, if I use my left hand, can I point my thumb in the direction of the electron flow current? Yes. But we're going to do everything with conventional current and with our right hand. Fingers are going to wrap in the direction of a magnetic field. So let's see how this works on some diagrams below. The right-hand rule applies to conventional current. I already alluded to this, and you can use your left hand if you wanted to do it according to electron flow. So it says here to draw the magnetic field lines around each wire below. Well, this first wire we know that anytime we have a wire, we're having this magnetic field that's in concentric circles around the wire. And then that is going to get weaker and weaker the further we get away from the wire. So those magnetic field lines will space out more and more the further we get away from the wire. Eventually that magnetic field is not really going to be felt. But now we take the right hand rule, take your right hand, and because that means the current's going into the page, our thumb is going to point into the page, thumb in the direction of the current. Actually practice it yourself so you get familiar with it. Your fingers wrap in the direction of the magnetic field. So the magnetic field is in this direction. In other words, if we took a compass and we stuck a compass right there, we would find the north pole of the compass needle to point that way. If we took the compass and we stuck it there, the north pole of the compass needle would point that way. And the same thing out here. So that is the direction of the magnetic field in the first case. In the second case, again, we have these concentric circles around the wire, and they're going to space out more and more the further out I get, because it's getting to be weaker and weaker. But now we take our right hand and our thumb is pointing out of the page. Our thumb is pointing towards us. And we curve our fingers, and our fingers point in the direction of that magnetic field. And so the magnetic field now, in this case, is actually opposite. It's counterclockwise, whereas in the first case, it was in a clockwise direction. I'm going to add a couple more quick diagrams here, and that is just as I said earlier, we could have a current-carrying wire that somehow goes like so. So the conventional current is in this direction, and then we're going to have our thumb points in that direction, and our fingers are going to wrap down in front of the wire. So we're going to have this magnetic field that is coming down in front of the wire and going up behind the wire. Likewise, we could do something like this, and I could have a current that's going in this direction, and then you say, well, my thumb is in the direction of the current. My fingers, again, actually do this. My fingers are going to wrap coming up the front of the wire, going down the back of the wire. So the magnetic field is going to go something like that in that particular case. So we can change up the orientation, but the right-hand rule applies. We just have to turn our thumb in different directions and then curve our fingers. And however our fingers are curved is the direction of the magnetic field. So Ørsted's discovery can be used to produce magnetic fields with properties that can be controlled. We can control it based on how much current we pass through the wire, which can be controlled based on how much electric potential difference I have in my source. And so we have a bunch of ways to control that. We could also control the current based on how much resistance is in my circuit as well, because we know there's a relationship in Ohm's law, V equals IR. So depending on how we control voltage and resistance, we can control the current, which in turn will control the magnetic field. So interestingly enough, Ørsted is not really known as the father of electromagnetism. And the reason for that is because André Marie Ampere came along, and he actually showed that not only is a magnetic field caused from a current, but he showed that how we can actually get this magnetic field to work as a magnet. And so what I want you to do right now is these are two current-carrying wires. It's a conventional current. And in the diagram on the left, I want you to draw the magnetic field. Pause the video and do that. And then do the same for the diagram on the right. And then we're going to talk about what's happening in those two diagrams. So go ahead, use your right-hand rule, pause the video, and try this out. So hopefully at this point you have diagrams that look like this. In the first case, we have counterclockwise circles or magnetic field, and then followed by clockwise. And then in the second case, they're both counterclockwise magnetic fields. So why do we actually draw this? Well, it has to do with actually showing that we have this magnetic force. Ampere didn't just say, okay, well, what happens if I have these two wires? He actually was able to let those wires be loose and move based on the force they were experiencing. So what he found in this first case is the magnetic field is going in the same direction here, and he found that these two wires, as they were free to move, actually were forced in this direction. They were forced away from each other. And so the idea here is two parallel wires with currents in opposite directions repel. Two parallel wires with currents in opposite directions repel. Now you might be able to guess what's happening in the second case. Well, here we have these two magnetic fields are in opposite directions. And what happens here is we actually get a force of attraction between those two wires. And so we could say that two parallel wires with currents in the same direction, they attract. Same direction attracts, opposite directions repel. So that was the beginning of this whole discovery and use of these to build motors that we're going to look at in the days to come. So it also brings us to our second right-hand rule, and that is the right-hand rule for a solenoid. A solenoid first should be defined. So let's just look at what this looks like in this particular case. Simply put, before I get into the words, a solenoid is just a coil of wire. You can see there this wire is wrapped behind and back up in front and behind and back up in front all the way around this particular piece of metal that's in the shape of a cylinder. That is what a solenoid is. You don't need the piece of metal in the shape of the cylinder. You can just wrap the wire itself, but that is what a solenoid is. So a coiled conductor, also known as a helix or a solenoid, those are all the same thing. It behaves very much like a bar magnet. The location of the north pole of any current-carrying coil can be determined by using the right-hand rule for solenoids. Once again, mentally grasp the coil with your right hand. Our thumb is now not in the direction of the currents. Our fingers is in the direction of the current. All right? So our fingers in the direction of the current flow. Your thumb is going to point in the direction of the north pole in this case. So all we're doing is we're taking that idea of Ampere's discovery, and we're basically saying that down here the current's coming out of the page everywhere along there, and then at the top it's going into the page. So we could redraw this like this. We could say up here we're going into the page at the top. So we've got 4 wires at the top going into the page, and at the bottom we have 4 wires coming out of the page. And if we were to draw just like we did before up at the top, we would draw in every single one of these cases the current or the magnetic field is going in this direction. And we could also draw it like that. So magnetic field's going in that direction like that. And then you can see that every single one of these wires is going to cause the magnetic field here on the bottom to go to the left. Well, every single one of the wires on the top is going to cause the magnetic field goes down like that. So it's going to cause the magnetic field inside to go to the left as well. And if we continue that, we can see that. Continuing around that one, we can see that. And overall, what we can see is inside this portion, inside this solenoid, the entire magnetic field is going in this direction. Outside the solenoid, the entire magnetic field is going in this direction. Well, what does that look like to you? And out here, it's going in this direction. That looks like a bar magnet, and that's in fact what it's doing using Ampere's experiment. We're literally causing this piece of metal to become a bar magnet because we're running a coil of wire around the outside of that piece of metal. This is known more specifically as an electromagnet. And if we were in class, what we would be doing is I would give you a coil of wire around a bolt or a large piece of metal, and we would then connect it to a power supply, probably just a battery, and then you would just take that bolt and you would touch it to paper clips, and you would be able to pick up many paper clips because we formed an electromagnet using this discovery that Ampere had for us. So again, let's go over the rule. We put our fingers now in the direction of the electric currents, and our thumb is going to point in the direction of the north pole. So thumb is pointing in the direction of the north pole. Note that. All right, let's do a couple of examples now to wrap this up. The first one says this. In the diagrams below, indicate the location of the north pole. The first thing that we need to keep in mind here is what direction conventional current goes. Conventional current goes from it's the opposite direction an electron would move. And so an electron would be repelled from negative and be attracted to positive. So conventional current goes from positive to negative. So going from positive to negative is going to come down the front like so. And now you're going to use your right hand. No, not your left hand, your right hand. You're going to put your right hand in the direction of your fingers are going to wrap in the direction of the current. And your thumb is going to point in the direction of the north pole. So you're going to have something that looks like that. If that makes sense, go ahead and pause the video and try the next few examples and see if you get the same thing that I do. All right, so here are the answers for that. We're going from the positive to negative. So in this case, we're going up the front. So if I put my fingers wrapping up in front and going down the back, my thumb is going to point in this direction, which is the north, and by default, that becomes the south pole. Likewise, you can't really see it here, it's cut off, but you can see this is the negative side. So we're going again from positive to negative, so we're going this direction. And so if our fingers, using our right hand, our fingers are wrapping in the direction in front of the electromagnet, our thumb is pointing up, that's going to be north, that's going to be south. And last but not least, again, every time that we see a circuit, the longer side is the positive side of the battery. The way I like to remember that is if I have two lines, a positive, I can take that apart and I get two longer lines together, make it longer than a negative. That's just how I remember it. And so in this particular case, we're going from, again, positive to negative. So it's going up in this direction. And it looks very similar to the diagram we have up above. So this is north and this is south. And then what I have there at the bottom for you is just, again, a picture showing that the electromagnet and a bar magnet are very, very much the same when we do this and run a current through a solenoid. So I hope that's helpful. As always, reach out for help if you have questions. All the best with this.